welcome to the second lecture. Today we will study the Schwarzschild solution that we introduced in the previous lecture, and in particular we'll study its exterior, its physical properties, the geodesic motion, and we will also show that horizon is only a coordinate singularity. Good. So let's start with the Birkhoff theorem. So on the last lecture we have introduced the metric for the Schwarzschild black hole, and of course we have assumed that the mass is greater than 0. We will study the negative mass case in the next lecture. So the question is, so we have introduced this solution as an outcome of the spherical collapse, or a spherical collapse of a star. So we have the matter falling into a black hole as a completely gravitationally collapsed object, and the exterior, which is vacuum. And the Schwarzschild describes the vacuum solution. Now, the question is, are there other possible outcomes of the spherical collapse? For example, can there be some gravitational radiation together with the compact black hole object? And the answer is actually no. And it all comes to the Birkhoff's theorem. The Birkhoff has shown that the Schwarzschild solution is the unique spherically symmetric solution to the vacuum Einstein equations. So any spherically symmetric solution to vacuum Einstein equations is a metric to Schwarzschild. To the Schwarzschild solution. Let's quickly sketch the proof. And it will be an exercise to check it in full detail. So the first step of the proof is actually to write the metric in the convenient form. So since we want to show that a given solution is unique, we would prefer, and we are solving the Einstein equations, which have a lot of coordinate freedom, gauge freedom inside it, we would prefer to fix the coordinates as much as possible, to fix the gauge as much as possible. So there's a statement in the differential geometry that we can diagonalize any 2 by 2, any metric on a two-dimensional Riemann surface. Actually, the statement is stronger. We can diagonalize it with respect to any given non-constant function to be one of the coordinates. We can use it to diagonalize the block of t and r coordinates. So again, recall that in the previous lecture we wrote the metric of a spherically symmetric spacetime as r squared sine squared theta 0, 0. Here is nothing, and there is the block GTT, GRR, GTR, GTR. So, in fact, so what I'm stating is that this TR block can itself, that is TR block, can itself be diagonalized with respect to one of the chosen coordinates, one of the chosen functions to be the coordinate. So it's natural to pick the radius area function to be the coordinate, radius area function r to be the coordinate. So can always to So we have the metric written in the form So the statement of this claim, the statement and the proof of this claim can be found in differential geometry literature, or alternatively in the appendix C of Good. So now after fixing the coordinate, after fixing the coordinate freedom, we can then write the Einstein equations, and they actually solve quite simply. So the TR component immediately gives us that dt of GRR is 0. And then comparing the, so therefore we have that GRR is a function of R only. And then comparing ETT ERR, we find that GTT equals, so GTT TR equals 1 over GRR R times some function of time. Now, this function of time is actually gauge freedom, and it can be removed by the reparameterizations of the time coordinate. So it means that when we write GTT dt squared, we can then go to such that C of t is removed by introduction of new coordinates. So therefore we find ourselves with t squared equals minus 1 over GRR. Okay. Actually don't have space. actually testify it. Okay, so then we find ourselves that all given metric functions are independent of time, and therefore, by the previous lecture, the metric is stationary and in fact static. So we have shown, and then we can use the result of the previous lecture, that any spherically symmetric stationary metric is isomorphic to Schwarzschild solution. Good. So this concludes the proof. Now, what does it mean in practice? So, in practice, we expect that the outcome of a spherical collapse of any reasonable matter would result in some compact solution, maybe some compact combination of matter, and the exterior, which is pure vacuum. So we have shown that however the spherical collapse is going, the exterior would be given by the Schwarzschild spacetime. So in particular, there is no spherical gravitational radiation. The stars cannot radially pulsate. Now, the spherical collapse itself is a well-studied model for the purposes of stability of initial data, and we will touch these subjects in lecture 4. Now let us study the redshift effect for the Schwarzschild solution. So, how do we do the setup? So assume we have some compact object, whether it's black hole or a star. And we have two observers, A and B. So let the observer A emit two photons, one after another. So let it be gamma 1. And let it be gamma 2. So from the point of view of the observer at the asymptotics, the distance between the time period between gamma 1 and gamma 2 is given by the interval between gamma 1 and gamma 2 is given by the delta t. Now, how long was the time period from the point of view of observer A? We need to compute the proper time, and the proper time is defined as interval over the world line of the observer A, which is actually nothing but, so we have 1 minus 2 m radius A over dt. This is constant, and we have it equal to square root minus 2m. Sorry. And we have it equal to 1 minus 2m r a dta. Similarly, the time difference with observer B is 1 minus 2 rb dt. Sorry, dt. So the relative time difference is then dTB over dTA equals 1 minus 2 mRA RB 1 minus 2 mRA. Now let us consider instead of single photons consider waves. So we can repeat the similar calculation for the two successive wave crests. So if from the point of view of asymptotic observer the difference between the two wave crests is delta t, then for the observer A it is delta tau A, and for the observer B is delta tau B. So we can find we can find the ratio of the periods. Now since we're using c equals to, since we set the speed of light to 1, the ratio of the wavelength is the opposite to the ratio of periods. So now let us consider the waves instead of the single photons. So we can repeat the similar argument, where now delta t measures the time interval between the two successive wave crests, as measured by the asymptotic observer. So therefore the period of a wave is delta tau, since the period and for the light the period is the same as the wavelength. So therefore we have the ratio of the wavelength given by the same value, 1 minus 2 mRB 1 minus 2 mRA. Note that since RA is less than RB, this is always greater than 1. So we have the wave. So the wave is undergoing a redshift. Now, if we take RB way larger, much greater than RA, which is greater or equal than 2m, we have lambda beta lambda alpha equals 1 minus equals So as we see, for the black hole, if RA is located at the horizon, the solution is, the wave is infinitely redshifted. If we consider a spherical star, then we have a Buchdahl inequality. The Buchdahl inequality, which bounds us from the previous lecture. We have R greater or equal than M. So for spherical stars, can never be greater than 2. Can never be greater than 2. Good. Let us now turn to geodesics in the vicinity of the Schwarzschild solution. First of all, let us write some integrals of motion. So, we have two commuting Killing vectors. That is k, which generates time translations. And we have axial Killing vector, which generates axial rotation. So we can therefore write the conserved quantities. So E equals minus k times u, where u is the flow velocity. So we have where tau is a certain parameter. So, and this equals to 1 minus 2 r dt d tau. And for the second Killing field, we have so the physical meaning of these two quantities is the energy energy per unit rest mass and the angular momentum per unit rest mass of the infalling particle. Of course, if you consider null geodesics, these two quantities are not physically meaningful because we have a freedom of reparametrizing the tau. For the null geodesics, these two conserved quantities don't have direct physical meaning because we have the freedom of changing the affine parameter tau. However, their ratio. So, however, if you consider their ratio the ratio is independent. So the ratio is independent under the changes of null parameter and is therefore physical. So we can interpret it as being the impact parameter, with the impact parameter that is the distance of the null geodesics from a line through the origin, and so the distance from a line of constant angle parallel to the geodesics. Now let us consider the axial dependence of the geodesics. So it is a nice exercise to find that the equation for the polar angle of the infalling particle is r squared d over d tau r squared d theta d tau minus h squared cosine theta sine cubed theta equals 0. equals 0. So one can define spherical coordinates. One can define spherical coordinates and polar angle in many ways. It is convenient for us to pick them such that theta equals 0 corresponds to the North Pole. Theta equals pi to the South Pole, and theta equals to pi over 2 is the equatorial plane. Note that this equation is smooth at pi over 2, and actually pi over 2 is a solution. So is a solution. So a radial infalling is indeed a geodesics as can be expected. So therefore we will always assume that the particle is that a radially infalling particle is moving in the equatorial plane. If it's not, we can just reintroduce the spherical coordinates such that the axis of rotation is orthogonal to the surface to the plane in which the particle moves. So, okay, it's a nice exercise to derive the radial equation, for the geodesic motion. So, first of all, let's choose the affine parameters such that G mu nu U nu equals minus sigma equals +1, 0, -1 for time-like. Now, space-like geodesics. Then, the radial equations of motion can be formulated in terms of some effective potential. So we have this equation can be derived from this constraint, from this integral of motion as well as from the integration of the geodesic equation. So we see that we have an effective So we see that we have an effective potential that is null at R that is null at 2m and plus infinity. So we have it growing to some constant value and then falling as r squared. Now, let us introduce a convenient coordinate chart that describes us the motion of an infalling observer. These coordinates are called Eddington Finkelstein coordinates. So let us now consider the radial null geodesics in Schwarzschild metric. So radial means that d theta d tau equals d phi d tau equals 0. Theta, for simplicity, we take to be the equatorial plane. So we can rescale the coordinate tau. We can rescale the parameter tau such that energy equals 1 minus 2 mr dt d tau equals 1. Then the condition for the roll line to be null reads as g mu nu u mu u nu equals 0 equals minus 1 plus dr d tau squared. So from this we have dr d tau equals 1. Yes, and from this we have dt d tau equals 1 minus 2 mr minus 1. So dividing one by another, we get that dr dt equals plus or minus 1 minus 2 mr, and plus or minus sign corresponds to either infalling or outgoing photon. So the right hand side, the right hand side turns to 0. The right hand side turns to 0 at the horizon, and therefore, if we treat it as t equals t of r, the time diverges logarithmically there. So to investigate what is actually happening at r equals to m, we would need to introduce a new coordinate. So this coordinate is called Regge-Wheeler radial coordinate. So diverges. So we can introduce a new coordinate dr star given by dr over 1 minus 2 mr. So integrating this, we get that the coordinate is given by r plus 2m logarithm r 2m minus 1, where we have where we have chosen the integration constant. So we're interested in the ingoing. So we're interested in the ingoing geodesics. And know that for large radius, this coordinate, regular radial coordinate asymptotes to the standard radial coordinate. So the radial geodesic equation then simplifies. So we have dt over dr star equals to plus or minus 1 depending on the direction. So therefore, integrating it, we get t minus plus r star equal to some constant. Let us actually define the new coordinate that corresponds to the infalling null geodesics. So we have v equals t plus r star. So v equals constant. So v equals constant corresponds to a radial ingoing null geodesics. So in v r theta phi coordinates. So in v r theta phi coordinates, the metric then writes as ds squared equals to minus 1 minus 2 m r dv squared plus 2 dv g rho plus r squared g omega squared. So this set of coordinates is called Eddington Finkelstein coordinates. Finkelstein. So as you can see, it's already a step forward. We don't have, so the metric is not single. The metric is no longer singular at r equals to m. And in fact, it's not even degenerate there. One of the consequences is that if we compute the curvature, the scalar curvature invariants, they should be regular. Good. So as we said, this metric is regular and non-degenerate at r equals to m, and in fact, it means that the spacetime itself can be extended past the horizon. So past the horizon. In fact, as we see, all the components of the metric are real analytic, and therefore, if we take their derivatives, in particular if we compute the curvature scalars, they should be real and analytic. They should be real analytic everywhere. Real analytic as well everywhere except at r equals 0, which for now we exclude from consideration. How does this metric agree with the Birkhoff theorem in the interior of the solution? So it's actually a good exercise. To go from Eddington Finkelstein to standard Schwarzschild coordinates in the interior region. So in r less than 2m region, go back from V R theta phi to T R theta phi. Check that we recovered the Schwarzschild. Geometry. But the radius now is less than 2m. So recover Schwarzschild with r less than 2m. Now we have shown that r equals 2m is regular. What happens at r equals 0? So let us compute the curvature invariance. One of the invariants is the Kretschmann scalar. And after the computation, we find that it is something m to the power of 2 r to the power of 6. So this definitely diverges as r goes to 0. So this is indeed some pathology. It's not just a curvature singularity that can be removed by the introduction of appropriate coordinates. This is an essential curvature singularity that will stay in any coordinate chat. So even more strictly speaking, we would actually not include the singular point into our manifold. So we have radial coordinate going from strictly greater than 0 to infinity. So what happens with the timeline killing field? So we had k equals d over dt, and upon converting to Eddington Finkelstein coordinates, we have equals to equals d over dv. So we can use this equation to extend the definition of k to the interior region as well. Note that k squared equals GVV. Note that at r equals to m, our killing field becomes null, and for the interior region, it becomes space-like. So r equals to m, k is null. Space-like. So therefore, in the interior region, we cannot say that the space-time is, strictly speaking, stationary or static. Now that we have introduced ingoing Eddington Finkelstein coordinates, let's see what happens with other radial null geodesics. So it is a good exercise to see that radial null geodesics belong to one of the three types. So we have ingoing we have the solution when where the geodesic is located at the horizon, and we have the outgoing one. So we have T minus R star, which equals to V minus 2R star equals constant. So I'll put outgoing in commas because, as we will see, if they start from the interior region, they're still not leaving the black hole. So from this follows that V equals to 2R plus 4M logarithm plus constant. Let's plot it. So it is convenient to introduce a slightly different coordinate, which is the difference V minus R, and on the argument axis we have R. So let this be the 2M, the horizon, and R equals 0. This is then the singularity. So in this chart, the ingoing radial geodesics are simply lines at 45 degrees. So we have the outgoing ones have a different plot between the two regions. So if we start with a point in the exterior, the trajectory goes as this. And in the interior, we have, let's take different color. So these are outgoing. As we can see for the outgoings, the radial coordinate is increasing if R is greater than 2M, and decreasing if R is. So we have that the outgoing geodesics starting behind the horizon, remain in that area, and eventually fall onto the singularity in a finite value of their affine parameter. So what happens with the general time-like curve? Let's draw the light cones. So here the light cone would be between the... So the light cones are formed by the two null directions. So in the exterior, we have light cones directed by this, and here we have light cones like this, as this. So any possible time-like curve, being geodesic or not, would lie within the light cone, and therefore also falls onto the singularity. Therefore also falls onto the singularity. So the question is, does the radius? So the question is, does the radius? So the question is, does the radius decrease for any possible causal curve? For any possible causal curve within the So the question is, does the radius decrease for any possible causal curve starting in the interior region? And the answer is yes, as we will show below. Any time-like curve starting in the interior region would also fall onto the singularity. The question is, can we prove this? The question is, if the statement is rigorous, and as we will answer in the next lecture, yes. So we will show that that any time-like causal curve, where the time-like null curve starting in the interior region would eventually end on a singularity. So before considering the black hole region, let us consider a possible gravitational collapse in our Eddington-Finkelstein coordinates. So we'll deal with the collapse of a massive star, and we assume that the exterior is empty. So the exterior is empty, and the mass is located in the interior of the solution. So by Birkhoff theorem, we have that the exterior, being a spherical solution of Einstein equations, must be isomorphic to Schwarzschild. So let us draw the Finkelstein diagram describing the collapse. So let the blue line denote the surface of a collapsing star. So the blue region is the of the star, and it's not Schwarzschild in general. If you take a sufficiently heavy collapse, we assume that the horizon forms, so that we don't end with neutron or white dwarf, and we have that at some point some part of the interior of the star would be hidden behind the horizon until whole of the matter of the star falls behind it. And here we have the singularity. Now, so yeah, the exterior is Schwarzschild. So let's consider the outgoing geodesics from the surface of the outgoing radial null geodesics from the surface of the star. So in the exterior region, in the exterior region, they will again go to infinity. But in the vicinity, but behind the horizon, as we have shown, they should fall onto the forming singularity. So this behavior is again the one that we expect from the black holes. So that we cannot possibly send a signal from the interior region to the outside. So let us put it into a physical perspective. How long does it take for the gravitational collapse to happen? So how long does it take an observer starting in the interior region to fall onto the singularity? And the answer to the process is actually quite short. So one can show that the affine proper time of any possible massive observer, that is, the movement, the world line of the observer is described by a time-like curve, which doesn't need to be geodesic, is actually bound by pi times mass of the solution times the Schwarzschild mass of the solution. The equality happens only for the affine parameter along an outgoing radial null geodesics, which starts at the horizon. So if you consider the black hole of our solar mass, so tau is of the order 10 minus 5 seconds. If you consider a supermassive black hole of the size of the size 100,000 times solar mass, this would take seconds. If you take the heaviest known supermassive black hole, so that is of the order of 10 to the power of 10 star masses, masses of the sun. This would be measured in hours. This would be measured in hours. So in this lecture, we have shown that the Schwarzschild solution has an interior region which is physically relevant for an infalling observer, so that the horizon is only coordinate singularity. And in the next lecture, we will start by showing that if a causal observer starts within the horizon region, it will necessarily fall onto the central singularity.